Hello everyone and welcome back again. In the last video, we wrote the spectral decomposition of a normal operator A uh, in terms of this basis, and we also defined the operator function like this. Okay, now here we'll discuss a particular example that is given in the text. And it's also stated that this procedure can be used to define the square root square root of a positive operator. The logarithm of a positive definite this can be said also positive semi-definite. PSD, that means the eigenvalue is greater or equal 0, and in that case it is strictly greater than 0. And it makes sense because the logarithm of negative numbers are undefined, and also if you want to get real numbers for this root, then this a has to be positive semi-definite, so it makes sense. And also this procedure can be used the exponential shell of a normal operator. This particular example is given in the text, and these two example is given in the form of an exercise. So here in this video, I'm gonna discuss about this. So what was the particular example? So let me find a new space here. So the example was e to the power theta z is equal to e to the power theta 0 0 e to the power minus theta. So how this can be written? Again, I'm writing the spectral decomposition that we defined, and also for the operator function sum over a. Now we have to use these two things to write this matrix. So what is Z? What is Z here? Well, I hope you remember the Pauli matrices 0, 1, 1, 0, 0 minus I, 0, and sigma Z 0, sorry, no, 1, 0, 0, minus 1. So this particular matrix is actually Z. These polymatrices are very important if you are gonna study quantum mechanics, and it also prescribed that you memorize this matrix. But instead of literal memorizing, it's better to memorize these matrices by working on them. So you can memorize it by yourself, or you can decide to memorize it by working on them. So right now in this video, I'm going to deal with that particular matrix. And well, so here the Z is 1 0 0 minus 1. So this is the poly Z matrix, sigma Z matrix. Okay, and it's also given that this 0 ket vector and 1 ket vector are the eigen vectors of this Z vector. So how can we uh, utilize this fact? Because this will be our basis. I mean, this 0 and 1 ket will be our basis. So if we write this 0 vector as 1 0, and then if we apply this Z vector on this 0, then what we get? We get 1 dot 1 0, right? So this is our Z, this is our ket 0, and this is our eigenvalue 1, and this is again the ket vector. So eigenvalue for this vector, this ket vector 0, is 1. And similarly, if we write this ket vector as, I mean, this 0 and 1 are orthogonal to each other, so this will be 0 1. And if we apply this Z vector to 1 ket vector, Z operator, sorry, Z operator, not Z vector, Z operator to 1 ket 1 vector, then 1 0 0 minus 1 0 1, and we get the eigenvalue minus 1 0 1, and this is ket, and the eigenvalue is, so eigenvalue for ket 1 vector is minus 1. So we got the corresponding eigenvalues for this ket 0 and ket 1. Right. Now what's next? Now we'll define the outer product. This 0 0 is 1 0 1 0. It is 1 0 0 0, and outer product for this ket 1 is 0 1 1 0 is 0 0 0 1, right? Now what was our expression for the operator function? This, right? So we are going to put these eigenvalues here. I'm going to write it again. So okay, a fresh writing. So our operator is operator function is this, right? Oh, sorry. And now we are going to find function of z, which is e to the power theta z, right? At first, we know that the eigenvalues for this 0 ket is 1, and eigenvalue for this 1 ket is minus 1, right? Now we are going to use this fact. So what is our function here? I mean the value, I mean if we take input as 1 eigenvalue to this function, we get e to the power theta. And if we put e to the power a minus 1 as the input for this function, then we get e to the power minus theta, right? So now we are going to write this. So this will be like this: function of z is equal to function of 1 0 0 plus function of minus 1 1 get 1. And what is the value for that? E to the power theta. And we have got this outer product from here, right? Here, this and this, right? This is for the corresponding outer product. So 1 0 0 0 plus e to the power minus theta 0 0 0 1, and if we sum this, then we get e to the power theta 0 0 e to the power minus theta, which is equal to theta z. So that ends the video. See you in another video.